We cannot hear you very well.
Some questions. Can, do you have?
Yeah, I have one question about residue theorem. If integral will be bounded not like modulus of z equal to something, if it will be bounded, for example, from 0 to infinity, we will have this situation or not? Sorry, I can't hear you. You're bad.
Uh,
Okay, can you wish how it's called? Can we compute one? Thank you. Okay.
Hello.
No, it's bad still.
I'm so sorry. Okay, let's try.
Now it's better. Now I hear you.
Okay, that's perfect. I'm so glad. You know that the residue theorem is used for computing complex integrals like that you have told me earlier, but also it is used to compute real integrals. Not all the real integrals, but some of them. some of them. And we are going to talk about real integrals today. You studied 3 types of real integrals. You have studied 2 types in the last seminar, and we have to talk about one more type. The first type is represented by the integrals from 0 to 2 pi of a function which is given as expression depending on cosine of t and sine of t, x here represented, over q of cosine t, sine t, t. Or if you like, I will write it with x instead of t. P of cosine of x and sine of x over q of cosine of x sine of x dx is the same. Okay, let's see I. So let's talk about this type of integrals. I've told you that if you want to compute such an integral, you have to make a change of variable, of variables actually. Let's take a look at this integral. We'll denote e at ix by here x is something real because x is between 0 to pi and is something complex. Okay, so x is real, but z is complex. And from a real integral, you'll get a complex integral. Let's take a look at this change of variables. First of all, you have to see what the x becomes. And when you compute the derivative here and here, you get I times e at ix, because this is the derivative of this one, times dx equals the derivative of z is 1 times dz. So this one is, and get that dx is actually this one, which is over I. Okay, this is dx. Then you have to change the domain of this integral. You know that x, which is the variable, is in 0 to pi. Okay, so x is in 0 to pi. And the change of variables is e at ix equals. So from here, it means that z is equal to, I'm using Euler formula. This is sine of x plus I. And this is actually represented by cosine of x and sine of x. So when x goes from 0 to 2 pi, z will be all the points with the coordinates cosine of x, sine of x. So actually z will cover the entire trigonometric circle, because you know that on the circle, all the points have the coordinates cosine of x and sine of x, where x is the angle. So the radius will be 1, and the center is 0. So it means from this that belongs to the circle of center 0, 0, and radius 1. But 0 is 0 corresponds to the complex number 0. So it means that the domain of the new integral is this one, modulo z equals 1. Okay, this is the new domain. Because this is the equation of this circle. And now you must see how you replace cosine of x and sine of x. Cosine of x is e at ix plus e at minus ix over 2, which is e at ix is z. So this is plus, and this is z at minus 1, which is 1 over z. And then you get that this is z squared plus 1 over 2z. Okay, so cosine of x is z squared plus 1 over 2z. And x from the definition is e at ix minus e at minus ix over 2I, which is actually z minus 1 over z over 2I, which is z squared minus 1 over 2z. So sine of x is z squared minus 1 over 2z. And now I will be this integral. So instead of this domain, which is 0 to pi, you will have this new domain, which is modulo of z equals 1. Instead of p of cosine, you will put p of z squared plus 1 over 2z and z squared minus 1 over 2i. This will be q of the expression time. And instead of dx, I write dz over iz. So I have dz over iz. Okay? And this expression without dz will be a function f of z. And in the end, it will obtain an integral, which is computed using the residue theorem. So this will be computed using the residue theorem. And I'm going to write briefly the steps. So for step 1, you have to find the singular points of f, singular points by SP. Step, you have to find the position of the domain bounded by the circle, which is given by this one. And you have to find which singular points belong to D. Step 3. For the points in compute the residue of f. Step 4, I is the sum of residues computed step. Okay, these are the steps that to follow in order to find the value of this I. And in the end, you must obtain something real, but just in this case, because I at the beginning, I from the beginning, was here. Okay, so this is because of the fact that I this integral at the beginning was the real. Okay, let me write it this way because it's a very important tool, very important tool. Okay, so let's see some applications. Just a sec. Let me think. Sorry, cosine of x, not of c. Cosine of x. Dx over 3 minus 2 sine x. Okay. And this one. And this one. Okay. What you should do here? What you should do here? Let's say this is I.
Find the points.
Of which function?
Of 3 minus 2 sin x.
Second, you have real integral. In the high school, you have learned how to compute such integral. So I want to move to the complex case in order to use residues. So the first step of computing this integral is to make this change of variables, because I want to obtain from this integral something which is like this. But for this, I need to make this change of variables. So let's write the change of variables. Is given by E at x equals, and because we have the computation, I'll write directly that dx is dz over iz, because you knew that you know that dx has this expression from here. Then the new domain is this one, Then cosine of x is z squared plus 1 over 2c. And sine of x is z squared minus 1 over 2. And you get this is an integral which was computed on 0 pi, but will be computed on this new domain, which is a circle of center 0 and radius 1. Then, instead of cosine of x, here I will put z squared plus 1 over 2z. So this is z squared plus 1 over 2z over 3 minus 2 times sine, which is z squared minus 1 over 2z. And this x from here will be replaced by z over 5 times z over 5. And now you must make some computations. Let's say that you have a simplification here, then you have to make the simplification. So you will z squared plus 1 over 2z all over 3iz minus z squared minus 1 over iz from here times dz over iz, which is z squared plus 1 over 2z from here times the inverse of this fraction, which is iz over 3iz minus z squared plus 1, which is this one, times dz over iz. We have a simplification, and here integral from to copy this expression. So I have z squared plus 1 squared plus 1 over to the from here times this one. And in the end, this dz. Now, you have a minus which can be taken in front of this bracket, and you have modulo of z equals 1, and the function is this one over minus 2z times z squared minus 3iz minus 1. And this is actually to minus 1 over 2 times this one. And this was I. Okay, so you have that the integral from the beginning is actually minus 1 over 2 times this one. Now, you have to compute this integral using the residual theorem. So you have to denote this one by f of z. Let's denote this one by f of z. And now, in this moment, we are in this case, okay, when you obtained this function. And it will be computed using the residue theorem. So you have to find first the singular points of f, then to write the domain, and so on. Which are the singular points of this function? in order to find singular points, you have to solve the equation and take equal. So first z1 0, and then z squared minus 3 times z minus 1 0. In this case, that is this one squared, which is actually 3i squared, is the same with minus 3i squared, but I'm going to write it in this way. Minus 4a, which is plus 4, okay? So this is minus 9 plus 4 is minus 5. So this is 5i squared. I'll write. So that is 5i squared, actually. And you have that z1 is minus 3, which is 3i, plus square root of 5 times I up here over 2, because a is 1. So this is 3 plus square root of 5 over 2 times I. And z2 is 3 minus square root of 5 over 2 times I. Oh, sorry, let's say z2 and z3 because we already have a z1, okay? So let's say z2 and z3. And now you have 3 singular points. z1, z2, and z3. And this was step 1. Then we have to write the condition of delta, which is this one, and find which singular points from the one previously found are in delta. So let's see. You have to write the condition of delta. The condition of delta is taken from here, putting less than instead of equal. And you have to compute the module of each of these points. Module of z1 is module of 0, which is 0, which is less than 1. So z1 is in D, or delta, it doesn't matter. Module of z2 is module of module I1. This is a real number, which is also positive. So you that one is this one. Of course, it is greater than 1. So that z2 is not equal. And module z3 will be computed in a similar manner. And 3 means square root of 9, so this is also positive. And this is 3 minus square root of 5 over 2. But this is 2 point something, and this is 3 minus 2 point something, which is 1 point something, which is, sorry, 0 point something over 2. So this is 0 point something, which is less than 1. So it means that z3 is so it has 2 points. Let's go to step 3. At step 3, you must compute the residue of f for the points which belong to delta. But in order to find the residue, you must see what type of points do you have. So what type of point is z1 equals 0? What type of point is this one for f? tell me what type of point is this? When f of the limit when it goes to 1 from f of z. Here is f. So the limit when z goes to 0. This function. This is 1 over which is infinity, which means that z1 equals 0 is a pole. Okay, and what is the order of the pole?
1.
Yes, exactly, 1, because z appears here at the power 1, so the order is 1. And for z3, you have to compute the limit when z goes to z3 from f of z. And this will be actually z3 squared plus 1. I'm going to put it in this way. Over 3 times z3 squared times 3z3 minus 1. Okay. But now z3 is a solution of this equation. So if you replace here z by z3, you will get that z3 squared minus 3i z3 minus 1 is 0. So in this case, the denominator will be here equal to 0. So this will be something which is not 0 over which is again infinity. So you have that z3 is a pole. And can you tell me the order?
Again 1.
Yes, again 1. Why 1?
Because it's first power.
Yes.
Multiplicity is 1.
Why? Why is the order 1?
Algebraic multiplicity is 1.
Yes, because the algebraic multiplicity is 1. The idea is that this expression z squared minus 3iz minus 1 is written as z minus z2 over z minus z3 because z and z3 are the numbers. And because of the fact that bracket from is 1, it means that the algebraic multiplicity of this solution is 1 because the exponent of each bracket is 1. Okay, so you have that the algebraic multiplicity of z2 is 1 and the algebraic multiplicity of z3 is 1, and this is why the order of z3 is 1. Z3 is also a pole of order 1, but the idea is that z2 is in delta, so we won't use z2, just z3. But this decomposition is very, very important because you cannot compute the residue in z3 if you don't write this expression in this way. And now let's start computing the residue. So the residue of f of z in z equals 0 is limit when z approaches to from z minus 0, which is z, up to power 1, because 1 is the order, times f of z, which is this one. You have a simplification here, and then you get 1 over minus 1, which is minus 1, and this is the residue. Let's take a look at the residue of f of z when it goes to this. This will be the when z goes to z3 from z minus z3 power 1 times z squared plus 1 over z times z squared minus 3iz minus 1. And this is what I've told you earlier. If you don't use this expression for this one, you won't see the simplification. So in our case, we must replace this expression by z times z minus 3. You see that you have here the simplification. And you replace z by z3, you get z3 squared plus 1 over z times z3 minus z2. And let's see, you have z squared, which is this one squared. Okay, so this is square root of 5 over 2 times I squared plus 1 over. This is 3 minus square root of 5 2 times this minus z2. And this is 9 plus 5 minus 6 square root of 5 over 4. This expression, but I2 is minus 1, so this is minus this fraction plus 1 over, let's take here we have 3 minus square root of 5 over 2 times I times, and this difference is actually minus square root of 5i. But this minus with this one and this one give plus, and yeah, minus 40 plus 6 square root of 5 over 4 plus 1 over 3 square root of 5 times square root of 5 over. Okay, this is a real number. You could make here computations if you want, but I won't do them. But the idea is that you have a real number here. Okay. Let's take a look at this expression. So we computed actually the value of this integral. So let's check again the computation. Just a second. I have that something is not right. Just a second. So we have this one, this one, this one. Did we miss something here at the beginning? It seems that we haven't made mistakes. Okay, it's fine. But still the value could be something complex, so it's not right. This is not right. No, I that this is 1. This is 1. Let's make the computations till the end here, because I have the impression that this is 1, so the sum is 0. Otherwise, it is something which is wrong. So let's take a look at this one. So we have here minus 14 plus 6 square root of 5 plus 4 over 4 times 2 over square root of 5 times 3 minus square root of 5. You have simplification here. And you get minus 10 plus 6 square root of 5 from here over times 3 minus square root of 5 times square root of 5. So this is minus 10 plus 6 square root of 5. 6 square root of 5 minus 10, exactly. So our computations are correct, but I wanted to check again the computations, because if this one was not 1, let's say that this one was 2, then 2 minus 1 is 1, so the sum of the residue is 1, and then I will be 2 pi I, but I is a real integral, and it cannot be something which is complex. So it's fine. It's fine. Our computations are correct. So from here, this right, then take the here, minus 1 over 2, okay, minus 1 over 2 from here, and this integral is actually equal to 2 pi I times the sum of the residues. So that one is 2 pi I times the residue of f in 0 plus the residue of f in Z3. But this is 1, so this is minus 1 over 2 times 2 pi times 0. So 0, because otherwise, if you don't have here 0, you will get something with I, and is wrong. Okay, and I had the impression that this one is different from 1, so I thought that it was wrong, but no, this one is actually equal to 1, and the sum is 0, so it's perfect. It is something real. Okay. Okay, I is I. Yes. Oh, do you have a question? Well, if you do not have questions, please try to solve point B from here. Okay, just a second, sorry. Just a second. Right, point B. Let you 15 minutes to point B, and then we discuss. Have you finished solving point B? Have you finished solving point B?
Not yet.
Okay. Do you need 5 10 minutes?
Yeah, about 5.
5 Every
No.
let's see the first part of the solution, and then we'll discuss the remaining part, the one that you haven't solved yet. So, what becomes this integral I? What becomes I?
E at minus I x cos x over 3 minus cos x squared, or no. Should we also change variable for the denominator?
All of them, from denominator and denominator. So this is the domain, and let's take a look at the function. This is cosine over 3 minus cosine squared. So this will be actually, instead of cosine, put z squared plus 1 over 2z, right? And this is 3 minus cosine, okay, squared times dz over iz, because this was dx. Is this the function that you have obtained? Or at least at first, because I need to make here some computations. Let's take a look. This will be 5 by 2z. So z squared plus 1 over 2z over this is 6z minus z squared plus 1, okay, over 2z all squared times dz over iz. So this is z squared plus 1 over 2z times this 2z squared is 4z squared, and this is 6z minus z squared minus 1 from here times dz over iz. Z squared, z and z disappear from here. 2 and 4 will simplify. So we have 2. And in front of this integral, I could write 2 over an I from here. And from here, I get a minus. And this will be actually z squared plus 1. This 2 came here. Oh, this is z squared plus this squared. Squared, so I would get a minus. I have a plus. This was squared, so I have z squared minus 6z plus 1 squared. Okay. My mistake, I forgot to write here squared, so you have to put here this one squared, and I don't have a minus to write in front of it because square has a minus, but this power is 2, so this minus will disappear, and I have this expression with plus and a dz in the end. And this is the function f of z. So in this moment, you exactly here, which is okay, you have this thing, which is a complex, and compute the residue thing. So 6 points of this points of f. Did you find the singular points of f, or you obtained a different function?
3 minus 2 square root 2 and 3 plus 2 square root 2.
Let's see. Let's make the computation. So you have z squared minus 6z plus 1 equals 0. That is 36. This one 30 minus 4. So it's 32. And you want to find the heuristic plus 32 plus 2. This is actually 16 times 2. So you have 4 square root of 2 over 2. And this is 3 plus 2 square root of 2. This is exactly what you have told me, right?
Yes.
Okay. So these are the singular points of f. Let's move to step 2. We have to find the condition of the domain bounded by the circle, that is. That's because the domain is not the circle. The domain D is actually the interior of the circle, which is this. So modulo of z1 is 3 plus 2 square root of 2, and because this is the positive, it is 3 plus 2 square root of 2, which is greater than 1, and modulo of 2 is modulo of 3 minus 2 square root of 2, which is 3 minus 2 square root of 2, because this is square root of 9 and this is square root of 8, so the difference is positive, and this is actually square root of 9 minus square root of 8 is something is 1, so just z2 is in D. Okay, z1 is not in D, but z2 is in D. Have you obtained the same result until now?
I haven't computed it. I was before it.
Repeat, please.
I didn't come to this point.
Oh, okay. Step 3. Step 3. Let's find what type of singular point is this one. What type of singular point is Z2?
All of order 1.
Pole of order
1.
more than take the
2.
yes, because z squared minus 6z plus 1 squared is z minus z1 times z minus z2 all squared. So it is z minus z1 squared times z minus z2 squared. Okay, so 1 to are both of order 2 because of this exponent. So you have that z2 is pole of order 2. Then I will let you 5 minutes to compute the residue of the function f in z2, which is pole of order 2. Okay. Try to find the residue of f in z2. Have you computed the residual? This is the formula that you have to use to find the residue. How did you compute this derivative of this function? You did what first?
We change z squared minus 6z plus 1 squared to z minus z1 squared multiplied by z minus z2 squared.
Perfect. So this is the limit z2 from z minus z2 squared times z squared plus 1 over z, z minus z1 squared times z minus z2 squared. And then you have to take the derivative of this. So you have a simplification here, and you have limit when z goes to z2 from, you have f over g. So this is z squared plus 1, the derivative, which is 2z, times z minus z1 squared minus z squared plus 1 times, and the derivative of this function will be the derivative of this function. So you have the u squared, okay? And squared derivative of this is 2u times derivative of u. z1 is the number, z is the variable, so this is 2 times u, which is z minus z1, times the derivative of this one, which is 1, okay, over z minus z1 squared, which is z minus z1 to the 4. Now, you have that this when z goes to z2 from, you have multiplication here. So you have 2z times z minus z1 minus 2 times z squared plus 1 over z minus z1 cubed. And this is 2z2 over z2 minus z1 minus 2 times z2 squared plus 1 over z2 minus z1 cubed. And this is 2z2 squared minus 2z to z1, then minus 2z2 squared from here, minus 2. And in the end, you have minus 2 times z2 times z1. This one times this one. Minus 2 from here over z2 minus z1. Cubed, which is minus 2 times, this is 9 minus 8, which is 1, minus 2 over, and the difference is minus 4 square root of 2 over 3. Okay, so this is minus 4, and this is minus 4 cubed times 2 square root of 2. This is 1 over 16 times 30 square root of 2. And the residue of f in 2. And now, in the end, you have that this integral is 2 pi I times the residue of f in z2, but you have a 2 over I in front of it, so I from here is 2 over I times 2 pi I times the residue. So I will be 2 over I times 2 pi I times the residue of f in this point. This is the theorem, which is 2 over I times 2 pi I times this one, which is 1 over 32. And it's very important. Tell me if you have questions. Do you have questions? Do you want me to give you an example which is similar to the one worked together to work by yourself? Or do you think that you understood and this is enough for this type of integrals?
I think it's enough.
Okay. Let's move to integrals of type 2, which are integrals of type I1, which is minus infinity and infinity. And here you have a polynomial p of x, or polynomial q of x, times cosine alpha x dx, where r2 is integral from infinity to infinity from p of x over q of x times sine of x dx. The steps are following. Consider f of z, which is p of z over q of z times e at I alpha z. Alpha is a real positive number. find singular points of F and choose singular points from the upper half plane. Step 3. Compute the residue of F in the singular points which are in the upper half plane. And step 4, I1 is the real part of 2 pi I times sum of residues. And I2 is the imaginary part of 2 pi I times sum of residues. Let's see some examples. Polynomial P and Q must satisfy some conditions, but you will see that in all the applications that you will see at the seminar, you will have all the conditions fulfilled. So what you should do here, what you should do at A. Who is P, who is Q, and who is alpha? P is polynomial P is X. This expert suppose is P, Q, and alpha is step. F P over Z times I times alpha. This function. P was Z because I must use complex variables. Q is Z squared plus 4, and this is E at I times 2 times Z. Step 2. Singular points of F. You have Q, which is minus 2, and 2, which is 2. Which one is in the upper half plane?
Z2.
Z2, because the imaginary part of Z2 is 2, which is positive. So it means that Z2 is in the upper half plane. Okay, but this one is not here. Let's go to 3. You have to find the residue of f of z in z equals 2i. What type of point is 2i, which is z2? What type of point is this one for the function f here?
Polar order 1.
Yes, it's a polar order 1. Because z squared plus 4 is actually z minus 2i times z plus 2i. And this power is 1, so it will be polar order 1. Well, the residue of the function z in z equals to I will be limit when z goes to 2i from z minus 2i times the function, which is this one. And what you should do to have a simplification? What you should do now with the function? What here to simplify? Right. You have to compute an integral with sign. So this will behave like I2 from here. And I2 is the imaginary part of 2 pi I times the sum of the residues. So this I here is actually, I'm going to write in this way, is the imaginary part of 2 pi I times and the imaginary part is this one. Okay, so I has this value, which is a real value. Okay. What you should do at point B?
The same. I mean, identifying P, Q, and alpha.
Yes, but you okay, sorry. Let's put 0 infinity, not minus infinity infinity. Because I want to solve an example when you don't have the interval minus infinity, infinity. Okay, that b with minus infinity here will be your homework. But now I want you to solve this problem. In this case, you should know this function by g of x, and you should check if g is even. G of minus x is 1 over minus x squared plus 9 times cosine of minus x, which is 1 over x squared plus 9 times cosine of x, because cosine is a given function, which is g of x. So that g minus x is g of x for each element of x. You should use this property. So in your case, I, which is integral from 0 to infinity from g of x dx, will be 1/2 of this one. You should compute this integral using the algorithm as you've seen before, and should divide it by 2. Okay, so let's say that this is I1. So this expression will be 1 over 2 times I1. And if you want to compute I1, then you have to identify P. P will be 1. Sorry. Q will be x squared plus 9. Okay, so now for I1. And alpha will be 1 because x here is multiplied by 1. So, step 1. Consider the function f of z, which is 1 over z squared plus 9 times the alpha, which is 1 times I times z. Step 2. Find the singular points of f. This one is in the upper half plane. This is not. Step 3. And you have a pole of order 1, and the residue of f in 3i will be the limit when z goes to 3i from, let's write this way, from z minus 3i times this one, which will be written as z minus 3i times z plus 3i over this one. And 4, let's find I1 is the part because it contains cosine is the real part of 2 pi I times this residue. We have a simplification here and here, so we get pi e at minus 3 over 3, which is real, and this one. Okay, so this one, but now we have to get I1. I is 1/2 from 1. Okay, so I is 1/2, which is p e at minus 3 over 6, and this is it. So you have questions. Then you don't have questions. Let me do the end of this. Sorry. Okay, let's check the attendance list. Okay, I have talked to you a lot, so I know that you're here. Udre Alberto,
Present.
okay, I have talked to you also. Pica Eduard, no, or maybe your microphone is not working properly. Ștefănescu Bogdan,
Here.
okay. Ana, maybe your is not working. And Zafar that he left the conversation. Okay, do you have questions?
We'll do some more exercise of the second type at the seminar.
We have talked about the second type of the seminar, but we haven't had so much time. Next time, I mean this week, we'll talk about integrals of order 3 and meet again integrals of order 2, of type 2, actually, when we'll talk about Fourier transform in 2 weeks. So type of order 2 will be meet again in 2 weeks.
All right, thank you.
Welcome, and maybe then you will see more examples. Okay, questions? If not, thank you. Have a nice evening and have a nice week too.
Thank you.
Goodbye.
Have a nice week. Bye.
Thank you. Goodbye. Have a nice week.
Thank you.